deepest secrets of the universe. But when this technological marvel looked at our nearest star, what it saw was not a planet, but a ghost. James Webb detected a giant planet candidate in 2024, the mass of Saturn. A moment of triumph. But when the telescope looked again months later, that planet was not there. This is not the only paradox of the system, because the planet orbiting the other star, despite being in the habitable zone, is battered by more than 463 documented flares from its star. But this leads to an even more fundamental question. And if you find these seemingly impossible mysteries exciting, then join this channel, because in a moment, you will see where a lost planet might have gone, and why that should worry all of us. We are beginning. For years, we thought the nearest star system should be one of the most promising places to search for life in the galaxy. Because, on paper, everything looked perfect, just 4.24 light-years away. A system of 3 stars. There was even a planet orbiting one of these stars in the habitable zone. That magical region where liquid water could exist on its surface. But as we looked closer, this promising picture gave way to deep concern. Because our closest neighbor was not a sanctuary. It was a trap. We now know that the more we study Alpha Centauri, the more complex and unsettling the picture becomes. Therefore, let's focus on what we do know. Imagine you are floating far beyond the outer edge of our solar system. Looking back at the nearest stretch of interstellar space, among the countless stars scattered in the darkness, one target stands out. It is not a single sun. It is a family. Alpha Centauri consists of 3 stars bound together by gravity, moving as a common system through the galaxy. Although we often speak of it as a single place, it is actually 3 distinct worlds of starlight, each following its own path around a shared gravitational history. At the center of interest is Alpha Centauri A. This is a G-type star, quite similar to our Sun. It contains about 1.1 times the mass of the Sun, and its surface temperature is roughly 5,790 Kelvin. If you were to replace our Sun with Alpha Centauri, since the change would be surprisingly subtle. Because, from the surface of the Earth, you would hardly notice the difference. Nearby is Alpha Centauri B, which is slightly smaller and cooler. This star belongs to the K-type star class. Its mass is about 0.91 times that of the Sun, and its light has a warmer, more orange-tinged hue. Many astronomers find these types of stars particularly interesting because they burn their fuel more slowly and can remain stable for longer than stars like our Sun. These 2 stars orbit each other in a long, elliptical dance. At their closest approach, the distance between them drops to roughly 11 astronomical units, which is equivalent to the distance between the Sun and Saturn. At their widest separation, they move apart to about 36 astronomical units. A full orbit takes almost 80 years, but there is also a third member. Far beyond the bright central pair lies Proxima Centauri, the closest star to Earth. This is a red dwarf with only 1/8 the mass of the Sun. Despite being our closest stellar neighbor, it is so faint that you cannot see it without a telescope. Its orbit is surprisingly large. Proxima orbits Alpha Centauri A and B at a distance of about 13,000 astronomical units. it takes an estimated 550,000 years to complete a single revolution. For this reason, for much of modern astronomy, researchers debated whether Proxima was truly part of the system. But in 2016, precise velocity measurements confirmed that it is gravitationally bound to the other two stars. The entire system is quite old. Current estimates place its age at about 5.3 billion years, meaning it is about 700 million years older than our Sun. This is the first major concept in this story, Proxima b. For nearly a decade, it has occupied a strange place in astronomy because it is the closest known exoplanet, orbiting the star nearest to our own. It is located in a region where liquid water could potentially remain stable. But almost everything we know about it comes from indirect evidence, pieced together from faint movements detected across interstellar distances. Its discovery came in August of 2016, during the Pale Red Dot campaign, an international effort focused on the nearest red dwarf star. Astronomers working at the La Silla Observatory in Chile used the spectrograph abbreviated as HARPS to study Proxima Centauri with extraordinary precision. They never saw the planet directly. Instead, they looked at the star. As Proxima b moved in its orbit, its gravity exerted a tiny pull on the star, causing a slight back and forth motion known as radial velocity. This shift was astonishingly small. Proxima Centauri was wobbling at only 1.38 meters per second, slower than an average walking pace. Yet, this tiny motion was enough. The results were published in the journal Nature, and within hours, the headlines spread across the globe. But what is truly interesting is the location of this planet. Proxima b orbits its star at a distance of only about 7.4 million kilometers. For comparison, the Earth orbits the Sun at about 150 million kilometers. This means Proxima b is nearly 20 times closer to its star than Earth is to the Sun. In most cases, such proximity would create a hellscape. But Proxima Centauri is not a Sun-like star. It is a dim red dwarf that produces only a fraction of the Sun's energy output. Therefore, the region where temperatures might allow for liquid water is located much closer to the star. Astronomers call this region the habitable zone, and Proxima b Negasitz, at least geometrically, lies within this zone. This brings us to a second and more troubling concept. A planet can be in the habitable zone, but still be extremely uninhabitable. This statement suggests a possibility, not a confirmation. As our understanding deepened, astronomers began to realize that Proxima b's greatest challenge was not its distance from its star. The problem was the star itself. From a distance, Proxima Centauri appears almost modest. Its light is faint. Its size is small. Even though it is the closest star beyond the Sun, you cannot go outside and find it with your eyes. But beneath this subdued appearance lies a level of activity that shapes almost every discussion about its planets. The source of this activity is magnetism. Proxima generates magnetic fields in its interior. But the behavior of these fields is much more chaotic. Twisted magnetic lines get tangled, stretched, housed, and compressed until an enormous amount of energy builds up in the star's atmosphere. Eventually, this stored energy is released in an explosive event known as a stellar flare. This brings us to the most fundamental concern: radiation. A planet's orbit is only 1/20th of Earth's orbital distance from its star. This geometry has consequences. Radiation follows a principle called the inverse square law. This means that when the distance doubles, the intensity drops dramatically. As you get closer, it increases at the same rate, at 1/20th the distance. The exposure is roughly 400 times greater. Now you can begin to see the problem. Imagine a flare far more powerful than anything modern humanity has witnessed from our sun. If Proxima were to release an event 10 times more energetic than the largest solar flares ever recorded, a nearby planet could receive about 4,000 times the radiation that Earth would be exposed to during an equivalent event. This was not just a theory. When researchers began a routine observation on March 24th, 2017, they did not know they were about to witness one of the most significant moments in the system's history. Because, on that day, Proxima Centauri literally exploded. The instrument responsible for this was ALMA. Spread across the high deserts of northern Chile, ALMA consists of 66 radio antennas placed in some of the driest terrains on Earth, working together. These antennas function as a giant observatory capable of detecting faint signals from distant regions of the cosmos. On that day, astronomers were not looking for stellar violence. But something unexpected erupted within the observations. The star suddenly flared. In less than 10 seconds, Proxima's emission at millimeter wavelengths increased by roughly 1,000 times. For a star already known to be active, the scale of the event was astonishing. Then it intensified further. The measurements showed a peak brightness about 10 times greater than the largest solar flares ever recorded from our own sun. It was sudden, intense, and extraordinarily powerful. But the event itself was brief. In less than 2 minutes, the flare had largely subsided. Therefore, at Proxima B's orbital distance, radiation from a flare does not dissipate into vast empty spaces before reaching the planet. It arrives quickly and intensely. The ultraviolet energy from an event of this scale would spread across the world with immense force. Any exposed organic molecules near the surface would be instantly damaged. This observation led to another conclusion. Because, before the flare, some astronomers hoped that ALMA would reveal dust structures around Proxima. Instead, the data showed no convincing evidence of significant dust rings. The most persistent was the statistical inference. This flare was not discovered during a decades-long dedicated monitoring campaign. It emerged during just 10 hours of observation. The researchers had just happened to be looking in the right direction. This completely changed the debate. Isolated examples were no longer wanted. Statistics were wanted. Scientists wanted to know if this flare represented an extreme outlier or a part of ordinary life around Proxima Centauri. So they watched. The results were published in the Astrophysical Journal in 2025. The number that emerged was striking: 463 flares. Not on geological timescales, judged not through indirect reconstructions. These were individual events detected during the observation campaign. Patterns soon became visible. The distribution followed a pattern that astronomers call a power law. Small events occurred frequently, while large events became progressively rarer. But there was a problem. The larger flares were appearing more often than previous estimates had suggested. ALMA was revealing a level of activity that previous surveys had not fully captured. This brings us to another major threat from the star itself. Radiation is only part of the story. There is another force at work every day, every hour. Astronomers call it stellar wind. Stellar wind is an outflow of charged particles that continuously flows from a star in all directions. These particles include protons, Seksh, electrons, Sekchi, and heavier ions, all traveling at immense speeds through the surrounding space. Our own sun also produces a solar wind that constantly sweeps through the solar system. Near Earth's orbit, this flow moves at about 1.6 million kilometers per hour. The Earth constantly experiences this pressure. But Earth has a defense. The planet's magnetic field creates a protective bubble called the magnetosphere. But what if this protection weakens or never develops? Models of Proxima Centauri suggest that its stellar wind could be dramatically stronger than the solar wind reaching Earth. Because, since the star exhibits such intense magnetic activity, researchers estimate that the particle flux could be hundreds or even thousands of times greater than what our planet experiences. The distance problem makes it worse. Proxima b orbits its host star at an extremely close distance. At this range, the particle flux is concentrated into a much smaller region of space. The atmosphere is exposed to a much more direct assault. This mechanism is known as atmospheric sputtering. Atmospheric sputtering occurs when energetic particles collide with gas molecules in the upper atmosphere, transferring momentum to them. Some molecules gain enough energy to escape the planet's gravity entirely. The atmosphere leaks into space, one molecule at a time. This process is not theoretical. We have a much closer example. Evidence suggests that Mars lost its global magnetic field about 4 billion years ago. Without this protection, the solar wind had direct access to the upper atmosphere. Over millions of years, a large part of Mars's thicker atmosphere was stripped away. Proxima b could be facing a similar challenge. The difference is, we do not know if it has a magnetic field. Current technology cannot determine the answer to this question. This uncertainty has become one of the most important unknowns in the system. When we bring all these concepts together, the picture becomes clear. The challenges surrounding Proxima b are not isolated events. They operate concurrently, overlapping over billions of years, steadily narrowing the margin for survival. The constant bombardment of radiation, the powerful stellar winds, a chaotic magnetic field. But now we wonder, is this just the beginning? Beyond all these theoretical dangers, how much darker can the actual findings within this system make this picture? Because when astronomers turn their attention to the other members of the system, the mysteries not only deepened, but they also became stranger. And just then, when the telescopes looked at the system again, everything became even stranger. Because after astronomers find one planet, they rarely stop looking. When one world emerges, attention naturally expands outward. New observations of Proxima Centauri accumulated, and this process gradually revealed something important. Proxima b was not alone. There was at least one more confirmed planet in the system, and evidence suggesting a possible third. This transformed Proxima from a single planet curiosity into a developing planetary system, whose history might be far more complex than initially imagined. The latest confirmed discovery was Proxima d. Its existence was announced in 2022 and later strengthened by independent analysis in 2025. The detection came from the espresso spectrograph, attached to the European Southern Observatory's Very Large Telescope in Chile. It was one of the most precise instruments ever built for measuring stellar motion. The signal was remarkably small. The researchers detected a stellar wobble of only 0.39 meters per second. This motion is slower than the walking speed of an ordinary person. But buried within this subtle shift was the evidence of another orbiting world. Proxima d has a minimum mass of about 0.26 Earth masses. This makes it about a quarter of our planet's mass and roughly twice the mass of Mars. At the time of its announcement, it became the lowest mass exoplanet discovered by the radial velocity method. Its orbit is exceptionally compact. A year on Proxima d lasts only 5.12 days. The planet orbits at a distance of about 0.029 astronomical units from the star, which places it even closer than Proxima b. Therefore, but the conditions there are violent. Current estimates place its equilibrium temperature at around 360 Kelvin, which is about 87 degrees Celsius. Exposed water at sea level pressure would boil, but Proxima d was not the last mystery of the system, because beyond the confirmed worlds lay a more ambiguous possibility known as Proxima c. Unlike its siblings, this object remains controversial. The evidence has repeatedly emerged, but certainty remains elusive. During 2025, researchers using a spectrograph known as NIRPS at the European Southern Observatory's 3.6-meter telescope studied the system again. Their analysis failed to directly confirm the proposed planet. However, a weaker signal emerged near the orbital period previously associated with Proxima c. It seems something exists, but whether that something is a planet, is comets, stellar activity, or some other phenomenon remains unresolved. And now for the real shock. Because in 2024, the James Webb Space Telescope detected a faint object orbiting the system's most sun-like star. At first glance, it seemed like the kind of discovery astronomers had hoped for. Then they looked again. The object was gone. Astronomy sometimes produces a result so strange that the initial reaction is caution rather than celebration. That moment came in August 2024. The James Webb Space Telescope turned its mid-infrared instrument, known as MIR-SI-NAT, towards Alpha Centauri A. Before any search could begin, the telescope needed to suppress the star's overwhelming glare. To achieve this, Volvo engineers used a coronagraph, an instrument that places an opaque mask over a star's image. And something appeared. A faint point of infrared light emerged from the processed data. It was about 10,000 times fainter than Alpha Centauri A and was located at a distance roughly twice that which separates the Earth and the Sun. No previous survey had recorded this object. It was not in any catalogue. No historical observation showed evidence of its existence. Therefore, the team requested directors' discretionary time on the James Webb Space Telescope. This category is reserved for observations considered too urgent to wait for normal programming cycles. The telescope looked again in February 2025. The object was gone. Perhaps there had been a mistake. Perhaps processing artifacts had slipped through. Another observation was made in April of the same year. Again, nothing. You can imagine the atmosphere surrounding these results. A possible planet signal had appeared around the closest sun-like star to Earth and then disappeared before anyone could confirm it. The team's paper in the astrophysical journal Letters described the situation with unusual directness. They wrote that they were faced with a case of a disappearing planet. This phrase instantly attracted attention. If the object was real, Its estimated mass is close to that of Saturn, meaning about 95 times the mass of Earth. But here, uncertainty clings to every aspect of the detection. Was the original light point a previously unseen planet following an unusual orbit? Or was it an unrelated background source that was temporarily aligned with the system? Or did some subtle instrumental effects survive the careful layers of analysis? The mystery continues. Because the object not only appeared, but it also disappeared. This made everything more complex, more inexplicable, and scientists were faced with a series of findings from not one, but two star systems that defied known physics. So how was all of this to be explained? Because, Wahas, the final and perhaps strangest piece of this puzzle was that strange radio signal detected in 2020, which forced scientists to pause for a moment and ask if they were facing something extraordinary. Therefore, to explain this mystery of the disappearing planet, scientists pursued a moving object. If something appeared in one observation and disappeared in another, where could it have gone? Researchers approached this puzzle through computational orbital dynamics, Sharkey's Rawasis, which studies how gravity shapes motion over time. The work quickly became massive. Every available constraint had to be included. The August 2024 detection provided a location. The non-detections in February and April 2025 provided additional limits. The gravitational influence of Alpha Centauri b could not be ignored. Moreover, any proposed orbit had to remain stable for millions of years instead of descending into chaos. The computers began to explore possibilities, not thousands, not hundreds of thousands, but millions. The researchers built vast libraries of potential orbital configurations, testing each one against the available observations. Most failed. But a significant fraction survived. The results revealed that about 52% of all stable orbital solutions consistent with the August detection also predicted invisibility during both subsequent observations. This finding completely changed the debate because the object no longer had to be explained away as a mistake. A plausible mechanism existed through ordinary celestial mechanics. In many successful simulations, the candidate planet was moving inward along an elliptical orbit. As the object approached Alpha Centauri A, it became increasingly difficult to distinguish its faint infrared glow from the surrounding starlight. Even the coronagraph had its limits. The mask blocks direct starlight, Schwarzschild, but extremely close objects can still be lost in residual glare and diffraction effects. In these scenarios, the telescope was working exactly as designed. The problem stemmed from geometry rather than instrumentation, but another clue came from the past. In 2021, astronomers using the European Southern Observatory's Very Large Telescope reported a transient candidate around Alpha Centauri A, known as C1. The evidence had been insufficient for confirmation, and the object remained ambiguous. But when researchers compared this previous signal with the James Webb detection, interesting similarities emerged. The possibility arose that both observations had seen the same world. If the 2021 candidate and the 2024 candidate represent a single object, the combined record includes 3 independent observations spanning 4 years. This significantly strengthens the planetary interpretation. According to these models, the orbit extends between roughly 1 and 2 astronomical units from Alpha Centauri A. Such a planet would likely be more similar to Saturn than to Earth, but its significance extends beyond the gas giant itself. Because large planets often have extensive moon systems, they can also coexist with smaller, rocky worlds closer to their stars. And then there was that radio signal. Sometimes the most intriguing discovery is not a planet or a star. Sometimes it is a single line on a graph. In April 2020, astronomers working with the Parkes Radio Telescope in Australia were making observations as part of the Breakthrough Listen project. The project sifts through vast amounts of radio data, searching for patterns that nature might struggle to produce on its own. Among these patterns, one category receives special attention: narrowband signals. A narrowband transmission occupies an extremely small range of radio frequencies. Most natural astrophysical sources produce broadband emissions, spread out over many frequencies at once. Therefore, a signal compressed into a very specific frequency window can instantly attract interest. During the observations of Proxima Centauri, researchers found exactly such a signal. Its frequency was measured at about 982.2 MHz. The transmission appeared unusually intense and distinct from the surrounding radio noise. But this alone was not enough. This signal behaved differently. The transmission appeared only when the telescope was pointed at Proxima Centauri. When the observations shifted elsewhere, the signal disappeared. The signal was named BLC1. In the following months, teams scrutinized every aspect of the detection. The frequency shift was measured. The instrument performance was examined. Alternative explanations were tested. Before publication, members of the collaboration were reportedly calling it the most compelling signal encountered by Breakthrough Listen. This description reflected the combination of unusual features present in the data. For a brief time, the possibility remained open. Could a technological source exist around the nearest star system? But sadly, as the investigation deepened, more evidence pointed to Earth. In 2021, the analysis was published in Nature Astronomy. The conclusion identified BLC1 as radio frequency interference. The exact origin was never traced to a single device with complete certainty. However, the evidence pointed to a terrestrial source associated with satellites or ground-based technology. The signal was not extraterrestrial. All these discoveries, the disappearing planets, the non-existent signals, showed us one thing: how incomplete our knowledge of our nearest neighbor is. And to fill this gap, we needed not just better observations, but also an understanding of the fundamental mechanics of these systems, the basic physical processes that make a world habitable or hellish. But how do the mechanisms behind all these discoveries and mysteries work? Let's slow down a bit now and dive into the depths of the technical to understand why this system is so alarming. Because it all begins in the star's youth, when astronomers discuss the future of Proxima. They often start with the world we see today. But a much deeper problem may lie much further back in time, long before any modern flares struck the planet and its current environment emerged. The story begins during the star's youth. Red dwarfs do not begin their lives in the stable state we observe billions of years later. Before they reach maturity, they go through a long phase known as the pre-main sequence stage. This term describes the long period during which a young star slowly settles into sustained hydrogen fusion. For Proxima Centauri, This stage lasted hundreds of millions of years, and during that time, the star was dramatically brighter. Current models suggest that Proxima may have emitted 10 to 100 times more energy than it produces today. Therefore, this changes everything about the early conditions experienced by nearby planets, including Proxima b. At its current orbital distance, the planet theoretically sits in the zone where liquid water could exist. But when you rewind the clock to the system's earliest history, the same location falls into a very different category: the runaway greenhouse zone. A runaway greenhouse occurs when the incoming stellar energy becomes so intense that surface water evaporates faster than a planet can cool itself. Water vapor then accumulates in the atmosphere. Because water vapor is also a greenhouse gas, it traps additional heat. More heat creates more evaporation. More evaporation traps more heat. The cycle feeds itself. When water reaches the upper atmosphere, another process begins. Ultraviolet radiation splits the water molecules into hydrogen and oxygen. This mechanism is called photodissociation. The consequences are severe. Hydrogen is the lightest element in the universe. Given enough energy, it escapes a planet's gravity and drifts into space. The original water cannot be easily reconstituted. It is lost. Models suggest that Proxima remained in this brighter state for about 160 million years. That is longer than the time that separates the extinction of the dinosaurs from the present day. This brings us to another inevitable mechanism: tidal locking. Imagine a planet where the clock has lost its meaning, not because time has stopped, but because one of nature's most familiar rhythms never occurs. There is no dawn breaking on the horizon, no evening falling over the landscape. For Proxima, this may be the reality. Because its orbit is so close to its star that gravity has likely altered the planet's rotation forever. Over billions of years, tidal forces have slowly synchronized the world's spin with its orbital motion. Astronomers call this state tidal locking. We already know one example. The Moon is tidally locked to the Earth. Whenever you look up, you see the same lunar hemisphere. Proxima b appears to have reached a similar arrangement. But the consequences are far more dramatic. One hemisphere constantly faces the star. The opposite hemisphere constantly faces away. A full revolution around Proxima does not produce a sunrise or sunset, because the same regions always occupy the same positions. Daylight becomes permanent. Night becomes permanent. On the star-facing hemisphere, the red dwarf hangs motionless in the sky. This completely changes the planet's climate. Between these extremes lies a remarkable boundary. Astronomers call it the terminator. The terminator is the ring around the planet where day meets night. Unlike the moving terminator that sweeps across the globe every 24 hours on Earth. This boundary remains fixed. If an atmosphere exists, the temperatures there might be relatively moderate. Some researchers view this as the most plausible region for long-term habitability. The weather would be unlike anything we know. Atmospheric circulation on Earth is driven partly by rotation and partly by uneven heating from the sun. On a tidally locked world, since the primary driver becomes the enormous temperature contrast between the hemispheres, heat constantly builds up on one side, while the other side loses energy to space. The atmosphere responds. Computer simulations predict persistent jet streams that transport heat along the terminator. Enormous circulation cells could stretch from hemisphere to hemisphere. Winds might blow continuously in preferred routes over geological timescales. But all these atmospheric and climatic mechanisms depend on a much more fundamental question. Does the planet still have an atmosphere? Because all the threats we have discussed so far, intense flares, a runaway greenhouse effect, powerful stellar winds, are aimed at a single target, destroying the atmosphere. And while there are some counter-arguments, the weight of the evidence paints a worrying picture. For example, some theoretical models suggest that the most energetic flares in red dwarf stars may preferentially erupt from the magnetic polar regions. If this pattern holds for Proxima Centauri, the most powerful bursts of radiation might not be distributed evenly in all directions. Since planets orbit near the stellar equator, some of the most violent emissions might be directed away from their orbital paths. However, this possibility remains unresolved. Observations published in 2025 using ALMA revealed unexpectedly complex flare structures. Researchers found evidence that the flare emissions might not be uniformly spread through the surrounding space. The subsurface could also be a refuge. Even if surface conditions are hostile, internal planetary heat could maintain liquid water underground. But how long can all these defense mechanisms hold up against a relentless assault lasting for billions of years? Because each mechanism in this system interacts with another, further narrowing that small window where life might take hold. And there are still other challenges we have not explained, particularly the complex dynamics created by the presence of the system's other stars, Alpha Centauri, A and B. And so, while we focus on Proxima Centauri, the other two bright stars in the system, Alpha Centauri, A and B, have been waiting for decades, almost tantalizingly out of reach. This irony has shaped much of modern exoplanet astronomy. Because Alpha Centauri, A is, in many ways, more remarkably familiar, classified as a G2V star. This G-type main sequence star closely matches the Sun's physical properties. Its surface temperature is about 5,790 Kelvin, while our Sun is roughly 5,778 Kelvin. Viewed from equal distances, distinguishing one from the other would challenge even experienced observers. You would see two nearly identical suns. Alpha Centauri B offers a different appeal. As a K-type star, it is slightly cooler, slightly less massive, and considerably longer-lived. Many astrobiologists find these types of stars particularly attractive because they emit less ultraviolet radiation and can remain stable for longer than stars like ours. But finding planets around these stars has proven to be extraordinarily difficult. The obstacle is not just distance, because the system is only 4.37 light-years away. Instead, astronomers face an observational problem created by the stars themselves. They are simply too bright. Any planet reflects only a tiny fraction of the starlight. Against the overwhelming glare of Alpha Centauri, A or B, isolating these faint signals becomes extraordinarily difficult. Searching for a planet is like trying to spot a spark drifting next to a lighthouse beam. The binary nature of the system makes things worse. Alpha Centauri, A and B orbit each other. When astronomers study one star, the other contributes contaminating light that must be mathematically subtracted from the data. Every measurement becomes more complex. Every potential signal requires additional scrutiny. This challenge contributed to one of the most famous false alarms in exoplanet research. In October 2012, a team announced the discovery of Alpha Centauri. B a small planet apparently orbiting Alpha Centauri b. But the excitement faded. Subsequent analysis revealed that the signal was caused by data processing artifacts rather than a real world. By 2015, the proposed planet was generally considered non-existent. Another challenge comes from geometry. A planet orbiting Alpha Centauri A at a distance roughly equal to Earth's distance from the Sun would appear separated by only about 3/4 of an arcsecond. An arcsecond is a unit of angular measurement equal to 1/3600th of a degree. Resolving such a separation is like identifying a coin from several kilometers away. The required precision is extraordinary. So, for decades, these obstacles have frustrated astronomers. The stars seemed promising, nearby, and familiar, but their planetary companions remained hidden. Until the beginning of 2024, there were no definitively confirmed planets around either Alpha Centauri EA or Alpha Centauri b. This was the landscape researchers faced when a new instrument finally turned its attention to the system. And this instrument had a mechanism that could change everything: coronagraphy. A coronagraph is a device that places an opaque mask over a star's image so that faint nearby objects can emerge from the glare. The process sounds simple, but it is anything but. Light does not move cleanly around obstacles. It bends, it spreads, it creates interference patterns called diffraction spikes that remain embedded throughout the image. But all these mechanisms pale in comparison to a much larger and more ambitious idea. For centuries, Alpha Centauri was a target for imagination more than engineering. Scientists calculated distances and lifetimes more, and often came to the same conclusion. The stars were reachable in principle, but unreachable in practice. Then a different idea emerged. In April 2016, investor Yuri Milner announced Breakthrough Starshot, a research initiative aimed at solving a problem that had previously belonged almost exclusively to science fiction. Its goal was surprisingly direct: to send a spacecraft to another star system within a human lifetime. The proposal almost immediately abandoned conventional spacecraft. Chemical rockets could never approach the necessary speeds, so the mission shrank much smaller. Instead of a large probe, researchers proposed fleets of gram-scale spacecraft called starchips. Each would consist of a small silicon chip carrying cameras, sensors, processors, and communication equipment. Each chip would be attached to a reflective light sail, an ultra-thin sail designed to capture momentum from powerful laser beams. The propulsion system is the heart of the concept, a ground-based laser array generating about 100 gigawatts of directed energy would fire at the light sails. The lasers would push the tiny craft continuously for several minutes, accelerating them to approximately 20% of the speed of light. This speed corresponds to roughly 215 million kilometers per hour. The fastest spacecraft ever launched by humanity. Voyager 1 travels at about 61,000 kilometers per hour. The difference is immense. At 20% of the speed of light, a starship could cover the distance to Alpha Centauri in about 20 years. But achieving speed creates new problems. Interstellar space appears empty from a distance. However, it contains dust particles and microscopic debris. At these speeds, even a grain similar in size to a bacterium carries the kinetic energy of a rifle bullet. A collision could instantly destroy a fragile probe. Even if the craft survived, another challenge awaits: there is currently no practical deceleration mechanism. The probes would arrive as fast as they departed. They would not enter orbit. They would not land. They would speed through the system. Every photograph, measurement, and observation would have to be made during a brief encounter lasting only minutes. All these technical challenges show just how complex a single problem is. But what is truly exciting is the big picture that emerges when we put all these pieces together. Because this system is not just a technical challenge. It is a laboratory where we ask the most fundamental questions about our place in the universe. And now, it is time to dive into the deepest and most controversial topic of this laboratory: the concept of the habitable zone itself, and the complex and often misleading realities that lie behind this simple phrase. And now comes the truly dramatic moment. Because, beyond all these technical details, a single phrase has shaped much of the public conversation about nearby planets. It appears in headlines, press releases, documentaries, and scientific papers. We hear it so often that it begins to feel more like a verdict than a starting point. The habitable zone. The name itself feels reassuring. Teobitast. But the term carries far less certainty than many people imagine. We are now reaching the climax. Because this simple concept itself may be the biggest obstacle, and also the greatest illusion, in our understanding of Alpha Centauri. In astronomy, the habitable zone is also called the Goldilocks zone. It refers to the range of distances from a star where a rocky planet could theoretically have liquid water on its surface. It is a useful concept. But it is also an incomplete one. Because the definition hides assumptions, a few of them. When astronomers calculate a habitable zone, they usually start with Earth-like conditions. The models assume an atmospheric pressure of roughly 1 bar. Greenhouse gases in a familiar range, and an atmosphere that can move heat around the planet. Change these conditions, and the picture changes. A world shrouded in a dense carbon dioxide atmosphere could stay warm much farther from its star. A planet with reflective cloud layers could stay cooler than expected. Remove the atmosphere entirely, and it becomes difficult or impossible to maintain liquid water, regardless of orbital distance. Therefore, distance alone cannot solve the problem. This distinction becomes important when we consider Proxima b. The planet meets the geometric requirement of the habitable zone. Its orbit places it in a location where liquid water could exist under the right conditions. But the conditions are unknown. No telescope has measured the surface pressure. No observatory has confirmed the atmospheric composition. We have never observed oceans, just clouds, rain, or even the atmosphere itself. Nearly a decade after its discovery, the central components required by habitable zone calculations have not been detected. This was the primary shock. The habitable zone was a promise, yes, not a reality. And for Proxima, that promise sounded emptier with each new piece of data. Because the early history complicates matters even further. Long before Proxima reached its current state, the star spent about 160 million years in a brighter evolutionary phase. During that period, Proxima b likely occupied a region where runaway greenhouse conditions prevailed. Water vapor would have accumulated in the upper atmosphere. Energetic radiation could have broken it apart, allowing hydrogen to permanently escape into space. The habitable zone eventually moved inward. But what was left behind? That question still lacked an answer, but the second and bigger shock came from the red dwarfs themselves. These stars were the most common type of star in the galaxy. They made up roughly 70 to 75% of all stars in the Milky Way. Most stars are red dwarfs. Most planetary systems orbit red dwarfs. Most of the potentially habitable worlds discovered so far belong to red dwarf systems. This makes Proxima Centauri more than just a neighbor. It is a test case. For years, astronomers saw red dwarfs as promising hosts for life. Their planets were easier to detect. The stars were small. The habitable zones were located close to the star, which made orbital periods short and observations easier. But convenience is not habitability. As evidence accumulated, a more complex picture emerged. Tidal locking seemed common. Intense flare activity seemed common. Atmospheric erosion seemed common. Long early brightness phases seemed common. The challenges discussed around Proxima b were no longer isolated concerns tied to a single world. They seemed systematic. This brings us to the third and perhaps most jarring reality. The comparison with the TRAPPIST-1 system sharpened this awareness. Located about 40 light-years away, TRAPPIST-1 is home to 7 Earth-sized planets, 3 of which are in the traditional habitable zone. When these discoveries were announced, many saw the system as one of the most promising places to search for life beyond Earth. However, the host star was another active red dwarf. The same questions returned. Could atmospheres survive? Could oceans persist? Could surface biology withstand repeated radiation exposure over geological timescales? The details differed from system to system. But the underlying concerns remained remarkably familiar. This was not an anomaly. This was a pattern. In science, patterns matter. One example can be dismissed as unusual. 2 nearby examples pointing in the same direction require closer attention. And this pattern was shaking our most fundamental assumptions about the possibility of life in the galaxy. Because if the most common type of star is systematically hostile to life, then the universe might be a much lonelier place than we thought. And the fourth epic moment came from Alpha Centauri, A itself. A calm, watch, sun-like star, far from Proxima's chaos. It should have been a refuge. But recent observations showed how fragile even this refuge might be. That disappearing planet candidate might not be just an observational error. It could reveal a deeper truth about the system's architecture. If a gas giant, the mass of Saturn, is orbiting in the inner parts of the system, between 1 and 2 astronomical units, it changes everything. The gravity of such a massive planet could make it nearly impossible for smaller, Earth-like planets to remain in stable orbits. Over millions of years, this giant planet would either eject them from the system or send them into a fatal spiral towards the star. The complete opposite of Jupiter's protective role in our solar system. Therefore, the search for an Earth in Alpha Centauri A's habitable zone could be thwarted by the very presence of a giant neighbor that destabilizes that zone. The place where hope was brightest might also harbor the greatest danger. It was a paradox, a dilemma, and it was the latest and most unsettling lesson that Alpha Centauri had to offer. Every finding, every data point, was leading us not to a more optimistic conclusion, but to a more complex and problematic reality. So what does it all mean when these findings come together? What does this tell us about the universe itself? Therefore, all these findings lead us to one of the biggest questions about the universe. A question that comes almost unbidden. We can study atmospheres, radiation, orbital mechanics, and planetary climates for years. But in the end, the conversation returns to a mystery that has persisted for generations. Where is everybody? This question is often known as the Fermi paradox, named after the physicist Enrico Fermi. During a conversation in 1950, Fermi reportedly summarized the issue with stunning simplicity. Given the size and age of the galaxy, intelligent life should have had plenty of opportunities to arise elsewhere. Yet, we see no clear evidence. It was impossible, but it was true. Astronomers listened to the sky, and all they heard was silence. The numbers behind the paradox remain striking. The Milky Way is about 13.6 billion years old. It contains at least 200 billion stars. Many have planetary systems. Thousands of exoplanets have already been identified, and the discoveries continue. The probability seems generous, if even a modest fraction of these worlds developed biology. And a smaller fraction produced technological civilizations. Then some societies should be much older than ours. Not thousands of years older, but millions or billions. A civilization with such a head start could traverse vast distances, alter entire planetary systems, or leave detectable signatures visible across the galaxy. But when we survey the sky, the expected evidence is missing. This silence was the universe's greatest record, the longest, yes, deepest silence in history, and the scientific world was shaken. Astronomers often frame this problem using the Drake equation, developed by Frank Drake in 1961. The equation does not provide an answer. Instead, it organizes uncertainty. Each term represents a step in the chain from stars to communicating civilizations. How many stars have planets? How many planets are potentially habitable? How often does life arise? How often does intelligence arise? For decades, exoplanet discoveries have encouraged increasingly optimistic estimates. Planets seemed abundant. Habitable zones seemed common. The galaxy seemed full of opportunities. But systems like Proxima Centauri complicate this optimism. Throughout this journey, we have encountered repeated obstacles: stellar flares, atmospheric erosion, periods of intense radiation, tidal locking, questions surrounding long-term climate stability. Each challenge reduces the number of environments where complex chemistry can thrive. These inferences extend far beyond a single nearby system. Because if red dwarfs, the most common stars that exist, routinely make life difficult, then several terms in the Drake equation shrink. The bottleneck may not be planet formation. The bottleneck may be planetary survival. This possibility strengthens an interpretation known as the rare Earth hypothesis. According to this view, Earth might occupy an unusually favorable combination of conditions: a stable star, a protective magnetic field, long-lived geological activity, a large moon, a relatively quiet cosmic environment. Perhaps such combinations are rare, but the opposite conclusion is equally difficult to dismiss. Even if only a small fraction of stars support life, the numbers involved remain enormous. There are 200 billion stars in our galaxy alone. Beyond that, there are roughly 2 trillion galaxies in the observable universe. Abundance survives even in the face of severe reductions. Alpha Centauri does not solve the Fermi paradox. Instead, it sharpens its edges. The nearest star system has turned a philosophical question into a measurable scientific problem, forcing us to examine which worlds can truly survive long enough for someone to eventually look out into the darkness and ask the same question about us. But now it is time to stop and think. All these epic discoveries, these staggering numbers, these shattered theories, they are not just abstract data. They are clues about our story, our place in the universe, and perhaps our future. Therefore, we must now slow down and ask what all this chaos means for us. What is Alpha Centauri trying to teach us? And that lesson might be far more unsettling than we hoped. And now we ask ourselves, what is our place in the midst of all this chaotic data? These impossible discoveries. It is time to stop and think. Because Alpha Centauri tells us not only about a star system, but also about us, the ones looking at that system. This is not just a scientific concern. This is a concern about our knowledge itself, a philosophical concern about what we are taught by what we see. Therefore, we now face the most important question. What is our nearest neighbor telling us about the universe? And more importantly, what is it telling us about ourselves? The answer to this question is hidden in the first great paradox: distance and understanding. On one hand, there is the mind-boggling scale of the physical distance to Alpha Centauri, 4.24 light-years. That is about 40 trillion kilometers. It would take humanity's fastest spacecraft, Kryugyuth Voyager 1, about 73,000 years to cover this distance. This is nearly 10 times all of recorded human history. Physically going there is impossible for our generation, and perhaps for many generations after. This is a tragic reality. Even the universe's closest neighbor is not a place we can touch, feel, or walk upon. It is an almost mythological destination, waiting at the end of a journey that would span generations. We are trapped on this planet, in this solar system, and even the nearest door seems locked. This is the most painful reminder of humanity's physical limitations in the universe. We are beings living on a tiny island in the middle of a vast ocean, and the nearest shore is a distance beyond our imagination. But here is the other side of the paradox. Though we cannot reach it physically, we can go there with our minds. This is a beautiful reality. We have built telescopes that collect photons from across a gap of 40 trillion kilometers. We have made instruments that can measure stellar wobbles of 1.38 meters per second, slower than a walking pace. We were able to record a star's brightness increasing 1,000 times in 10 seconds. This is a triumph of human intelligence. It is proof that our minds and the tools we create can reach places our bodies cannot. We may not be able to go there, but we can understand, interpret, and derive meaning from the light that comes from there. Therefore, you too are a part of this paradox. You too live on this earth within physical limits. But at the same time, while watching this documentary, you are traveling 4.24 light years away with your mind. You are thinking about the conditions on those planets, the dangers of those stars. This is one of the most fundamental human experiences, to be physically small but mentally limitless. But this brings us to a second and deeper contrast: loneliness and connection. On one hand, there is the potential cosmic loneliness that Alpha Centauri shows us. The fact that even the nearest star system is so challenging, so dangerous, and perhaps so lifeless, strengthens the rare Earth hypothesis. Perhaps worlds like ours, planets with this delicate balance that supports life, are indeed very rare. Perhaps in our galaxy of 200 billion stars, Finding a protected sanctuary like ours is harder than finding a needle in a haystack. This is a chilling thought. This is a tragic reminder of how vast the universe may be, but also how empty. There may be billions of worlds, but almost all of them might be either frozen, scorched, or washed in radiation. This shows how precious, and perhaps how lonely, our species and our planet are. This might be the universe's way of telling us, you are alone. But here is that but moment. This very sense of potential loneliness connects us more to each other. This is a beautiful reality. If life is rare, if worlds like ours are unique, then every living being on this planet, every person, every thought, becomes even more valuable on a universal scale. This is a truth that unites us. Because in this cosmic ocean, we are all in the same small raft. This shows how insignificant our differences are, and how vital our commonality is. The data scientists collect from a mountaintop in Chile, the signals a radio telescope listens to in Australia, all serve a single purpose: to understand our common home and its place in the universe. This is humanity's greatest collective effort. Therefore, you too are a part, and this brings us to one final contrast: knowledge and the unknown. On one hand, there is the incredible amount of information we have acquired in the last few decades. 20 years ago, Alpha Centauri was largely an imagined space in scientific discourse. Today, we can model atmospheric escape, predict orbital architectures, track stellar flares, and discuss the chemistry of distant worlds with remarkable specificity. Each measurement, each simulation, reduces uncertainty. The stars remain distant. The knowledge does not. This is the tragically slow, but unstoppable progress of human curiosity and persistence. Each answer often raises new questions, leaving us in a perpetual search for knowledge. But here is the beauty of this search. Certainty remains elusive. And this is not a weakness of science. It is the purpose of science. Knowledge rarely comes as a final answer. More often, large uncertainties are replaced with smaller, sharper ones. The frontiers of ignorance are pushed back, but they are never completely eliminated. Every advance in understanding reveals previously hidden details. Alpha Centauri has become an example of this process. Therefore, you too are inside this process. You are living at this very moment in humanity's effort to understand the universe. You are a generation torn from the certainties of the past, but not yet having reached the full knowledge of the future. You are living in an age where questions are more important than answers, and this is both a frightening and an exciting place to be. We now know that our closest neighbor acts as a mirror, showing us both how dangerous the universe can be and how precious our own planet is. We now know that our existence is based on both fragile coincidences and stable physical laws. But there is one more question. After acquiring all this knowledge, after diving into all these philosophical depths, what is our path forward? What will we do with this knowledge? Because the next step is not just to collect more data, but to look to the future and ask where this story is going. So now we face a deeper question. What will we do with this knowledge? Because when we look to the future, the landscape is changing. Many of the uncertainties we have discussed today are not waiting for new theories. They are waiting for instruments that are already being built. Tested, funded, or prepared for launch. The era of speculation is narrowing. This brings us to a new paradox: knowing the future and living the future. On one hand, there is the fact that within the next decade, we will have tools that will fundamentally change our understanding of the universe. In Chile's Atacama Desert, construction is underway on one of the most ambitious observatories ever attempted. The Extremely Large Telescope, or ELT for short, is being built with a primary mirror 39 meters in diameter. When scientific operations begin around 2028 Natsek, it will be the largest optical telescope placed on Earth. Its key instruments include METIS, which is optimized for searching for faint planets orbiting nearby stars. Alpha Centauri is at the top of the list. If there is a rocky world in the habitable zone of Alpha Centauri, A or B, METIS could separate that planet's light from the glare of its parent star. For the first time, nearby terrestrial planets could transition from theoretical objects to directly observed worlds. Another instrument, perhaps called Andes, could reveal whether Proxima b has an atmosphere and what its composition is. This is a tragic anticipation, knowing that the answers are just around the corner, but not being able to reach them immediately, seeing the door of knowledge ajar, but having to wait years to enter. But within this waiting lies a beautiful truth. It is proof that humanity can have a long-term vision. We are a species that can invest in projects whose results we may never see. The engineers and scientists building the ELT today are working for the discoveries that future generations will make. This is a collective project of humanity, where knowledge is passed on like an intergenerational torch. The breakthrough starshot concept also represents the same mindset on an even larger scale. If the concept succeeds, the people developing it today may never see the information sent back by the probes they helped design. Their efforts are directed towards a future they will not personally witness. Science often works this way. Therefore, you too are part of this long-term project. You are living in a time when these giant telescopes are being built, when these interstellar missions are being imagined. You are a witness to a moment when humanity is thinking not only about today, but also about decades, even centuries, from now. This is a hope that extends beyond time. This brings us to another contrast: perspective and reality. For a moment, reverse the perspective. Instead of standing on Earth and looking out, imagine yourself somewhere in the Alpha Centauri system. Looking back at the Sun through interstellar space, the view would be surprisingly familiar. From a distance of about 4.24 light-years, our Sun would remain clearly visible to the naked eye. It would not dominate the sky. It would not stand out as extraordinary. Yet, it would shine as a bright star with an apparent magnitude of about 0.5, or Keats, comparable to some of the prominent stars we easily notice from Earth. This is a tragic lesson in humility. That bright sun, which is everything to us, is just one of countless stars when viewed from another corner of the universe. Our cosmic center is just an ordinary point of light in someone else's sky. This reminds us how vast the universe is and how modest our place is. For a hypothetical astronomer, our solar system would be just one data point, one of thousands of systems to be studied. But within this humility lies a beautiful symmetry. If an astronomer there had roughly the same tools as we do, detecting Earth would not be particularly difficult. The immense mass of Jupiter causes the Sun to wobble slightly. Precise measurements could detect this motion. The same techniques that allow us to discover worlds around distant stars would allow them to discover our system. They could even study our atmosphere and find oxygen, water vapor, chud and methane. This would be a sign of biological activity. But even in this imaginary observation, there is a hidden limitation. Any astronomer studying Earth from Alpha Centauri today is not seeing our present world. The light reaching them now left Earth more than 4 years ago. Their view corresponds to a version of humanity that is already in the past. The same limitation applies to us. Therefore, you too are a part of this time delay. You, as you exist right now, cannot be seen from Alpha Centauri. The you that is seen from there is the you from 4 years ago. And when you look at Alpha Centauri, you are seeing it as it was 4 years ago. 2 potential civilizations, separated not just by space, but by time itself, each observing a version of the other that no longer exists. This is the most profound proof of how difficult a universal conversation would be. And this brings us to one final thought: the distant future of this system, Alpha Centauri. A will remain a main sequence star for about another 5 billion years. But it will eventually transform into a red giant. This transformation will change the architecture of its planetary system. The habitable zone will migrate outward. Regions that are cold and dark today may temporarily warm up. But Alpha Centauri. B will follow a different path because it burns more slowly. It can remain a stable K-type star for billions of additional years. And then there is Proxima. It is expected to continue shining for about 4 trillion years. This number is so large that it is roughly 290 times longer than the current age of the universe. This tragically means that even in a future where our star and planet have long since vanished, that little red dwarf will continue to shine. But in this longevity, there is also a beautiful hope. Even if the emergence of life is rare, these worlds receive immense cosmic timescales for evolution to experiment, adapt, and diversify. A low probability spread over trillions of years could produce outcomes that shorter-lived stars never experience. Therefore, you too are a part of this deep time. Human history is just a blink of an eye in the lifetime of these stars. But even in this fleeting moment, we can imagine, model, and understand those trillions of years of future. But these thoughts about the future bring us to the present moment, the final stop on this journey. And so, at the end of this journey, after all the measurements, models, detections, debates, and decades of observation, we arrive at the question that underlies it all. Why exactly are scientists concerned? The answer begins with what they are not concerned about. Alpha Centauri does not pose a threat to Earth. Its stellar flares remain confined to its own neighborhood. Radiation from Proxima Centauri does not threaten our atmosphere. The system's gravity does not have a meaningful effect from a distance of 4.24 light-years. Nothing that happens there puts our planet at risk. This is a tragic relief. Our greatest fears are unfounded. But this opens the door to a more subtle, more philosophical concern. Because the real concern is not a physical threat, but an informational one. This concern creates a new paradox: the weight of knowledge and the lightness of knowledge. On one hand, there is the heavy responsibility and potential disappointment that comes with the knowledge we have acquired. For generations, the nearest star system occupied a special place in scientific thought. If there was another living world nearby, Alpha Centauri seemed like a natural candidate. As instruments improved, the picture became more complex. Researchers studying Proxima b encountered flare activity far beyond anything Earth has experienced. Atmospheric models suggested significant risks of erosion. Simulations pointed to harsh early conditions during the star's youth. None of these findings alone rule out life. However, together, they form a pattern that is difficult to ignore. And this pattern might be telling a worrying story, not just about one world, but about the most common worlds in the galaxy. This is the tragic burden of knowledge. The more we learn, the more we understand how challenging the universe can be. Our hopes are tempered by the cold, hard reality of the data. But there is also a beautiful lightness to this knowledge. We are confronting the fact that Earth may not be a typical life-bearing planet. Our world benefits from a remarkably favorable collection of conditions. We orbit a relatively stable star. We have a long-lived magnetic shield. A regular rotation creates familiar day and night cycles. A large moon helps to stabilize our axial tilt. Each of these factors has been studied individually. Together, they create something rare enough to invite questions. But rarity is difficult to measure from a sample size of 1. This is why Alpha Centauri is so important. It offers the opportunity to compare our assumptions against another planetary system in extraordinary detail. The deepest concern is not that Alpha Centauri destroys life. We do not know if life ever arose there. The deeper concern is that the system might be revealing a broader truth about the galaxy. Perhaps building hospitable worlds is harder than we thought. Perhaps environments like Earth represent a rare outcome rather than a common one. This possibility presents a different kind of loneliness, not the loneliness of isolation in space, but the possibility that among countless stars, conditions like ours might be unusual enough to stand apart. This is a knowledge that makes us more humble, more careful, and more responsible towards our own world. Therefore, you too are balancing between this weight and lightness. You too feel the melancholy that comes with learning how vast and potentially empty the universe is. But you also carry the lightness and gratitude that comes from understanding how precious, how special, and how worthy of protection our own planet is. At the end of this journey, we understand one thing. This story was never just about Alpha Centauri. This story was always about us. In the midst of all this complexity, all this uncertainty, one truth shines through. What it takes to be able to learn all this. Every measurement we have discussed began with a person who looked up and refused to stop asking. The machinery behind these discoveries is extraordinary. But for all this precision, the nearest star system offered something unexpected, not reassurance, complexity. Its deep importance extends beyond astronomy. Underneath every observation lies a question larger than any planet or star. We are trying to understand whether life is a rare or common thing. We now know that our nearest neighbor is a laboratory that offers us the opportunity to ask this question not with imagination, but with evidence. We now know that our place in the universe is not guaranteed, but is a product of a series of lucky coincidences and stable physical laws. And we now know that this journey does not end here. Because, even as this story closes, the observations continue, the telescopes continue, the calculations continue, and the light continues. Across more than 25 trillion miles of space, information moves between one stellar neighborhood and another, linking two systems by the simple insistence of physics. And now, with all that we have learned, it is time to stop one last time and ask the ultimate meaning of this endless journey. We have reached the end of the journey. We set out to find an answer for Alpha Centauri. But instead, we returned with deeper questions. Our nearest neighbor showed us how complex the universe is, and how precious and fragile our own world is. You are now a part of this cosmic silence, and the curiosity that breaks that silence. Perhaps the greatest discovery is not what we find in the stars, but the fire within us that makes us look at them. And as long as that fire does not go out, our search will never end.